Let's see, is it working? Yes. Okay, so this brief panopto is to help finish up the lecture I was giving today, Thursday. Just want to begin this by mentioning how we incorporate radiometric dating and the physical stratigraphy, the physical relationships of rocks. You'll be doing this in the in-class assignment and the homework assignment for next week. So here we have this block of strata we saw before, and now we've added some information, and that is that this body of igneous rock is 235 million years old based on radiometric dating, and this body of igneous rock here is 198 million years old based on radiometric dating. In reality, there's plus or minus a certain amount. So now what does that tell us about the ages of this set of strata A, so the tilted beds down here, the set of strata B, and the set of strata C? Well, it tells us the stuff below, down here, A, is greater than 235 million years. How much greater? We don't know. Could be the youngest of these beds might be like just 1 million years younger, or it could be a billion years younger. We don't know, but we know it's older. So we at least have that information we didn't have before. How about these strata, strata B? Well, remember that this is an erosional surface at the base of B, and it cuts through this Pluton, this body of igneous rock, which is 235 million years ago. So it has to be younger than 235. It is also cut across by this bed, or by this igneous unit, 198 million years old. So that tells us it's between 198 and 235. Now, was it exactly one half the time in between? Or is it closer to one or closer to the other? We don't know, but we know it's between 198 and 235. And because the one that 198 is eroded, it's an erosional surface here that cuts through it, and C is deposited upon that, we know that C is less than 198 million years ago. How much less? We don't know. But at least we can now bracket the times that these are from. And then we would try to find additional information to maybe narrow down the individual times of these things. So that's how that works. Now in class, I did show how we could then tie these radiometric dates that we find at different areas into the index fossil based time scale to begin to put those data on there. And by the succession of doing this across the world in the 20th and now 21st century, we're able to get a far more precise dating of the boundaries of the geologic time units. Now, I mentioned a phrase, deep time, in the lecture this morning, and I didn't actually define it. Deep time is simply the vast expanse of time into the geologic past. And the radiometric dates, let's back up here, show that it's not merely a time of thousands of years, but it's of millions or even billions of years. And prior to radiometric dating, we didn't actually have a confirmation of how far back in numerical time these things were. But now we do, and we see the scale of it is vast. And that's why the nature writer, John McPhee, came up with this phrase, deep time. And he did so in analogy to deep space. So, we got Earth, and we've got Earth's orbit. That's in space. We got all the way to the Earth to the moon, as far as human beings have ever physically gone. And our objects have gone further, but our human beings have only been as far as the moon, the other side of it, technically. And that's near space. But beyond that, we get into the depths of deep space, the rest of the solar system, beyond our solar system to other stars, beyond other stars to the far reaches of our galaxy, and then galaxies beyond, and so forth. And the scale of that is immensely vaster than the distance between here and the moon. Similarly, although the times of, say, the European colonization of the New World, or the times of ancient Rome, or when the pyramids were being built in Egypt, seem vast to us as individuals, they are incredibly recent compared to the scale of deep time. So deep time, this vastness of geologic time. Now, there's another type of radiometric dating that is not like the others. So I mentioned the ones in class the standard model where we're dating igneous rocks. Specifically, we're dating igneous crystals in igneous rocks, and finding out about the time of crystallization of those. So we're not actually dating the fossils per se, but we're dating the age of the rocks in which they're found. And typically what we're doing is we're bracketing the age of the sedimentary units in which they're found by radiometric dates of igneous rocks above and below them. But there's a method where you can actually date the fossil itself. This is radiocarbon dating. It turns out that there is also, isn't merely that there's uranium and potassium and rubidium and so forth, which have radioactive isotopes. There's also a radioactive form of carbon, carbon-14. And carbon-14 naturally occurs. It continually gets regenerated in our atmosphere due to the effect of cosmic rays. And unlike uranium and rubidium, we're made of potassium to some degree. This is true. But we are made a lot of carbon. By we, I mean organisms. So radiocarbon dating, or carbon-14 dating, actually allows us to figure out the age of the fossil itself rather than the sediments they're in. And what we do is we can't actually compare the parent to daughter product. The daughter product of carbon-14 decay is an isotope of nitrogen. Nitrogen's a gas, it just goes back out into the atmosphere. What we do is we see how radioactive the object is. We can test how much radiation it still has. And that gives us a sense of how long ago it was that that particular organism was taking in carbon from the outside world, that is, alive. But this is limited in terms of the paleontological context, because the half-life of radioactive carbon, of carbon-14, is, as you see, around just slightly more than 5,700 years. It's useful in archaeology, so the study of human artifacts. It's useful in history. It's useful for the recent part, the youngest part of the ice ages, of the Pleistocene. But it's only good to about 70,000 years ago. Beyond that, there's not enough carbon-14 left in the fossil for us to directly date it. So it is useful for extremely young, from our point of view in paleontology, stuff. But it's useless if we're trying to date, a stegosaurus, or trying to date a trilobite. All that carbon-14 has long since decayed away. Now, there is another method we use of dating. This is one, again, where we're actually dating the rocks and not the fossils directly. And this has to do with an attribute of Earth's magnetic field. So as you all know, Earth has a magnetic field. There is a north and south magnetic pole, and that's what, when we have a compass, it's pointing towards the magnetic pole, not the geographic pole. The magnetic pole and the geographic pole are not quite the same. In fact, the magnetic pole moves around, even on a human time scale, but it's still close to. It's very high up in the northern hemisphere, and the magnetic south pole is very far south in the southern hemisphere. However, magnetic polarity can change. Geographic polarity doesn't. The physical north and physical south pole don't flip like that. But magnetic polarity can, and does. And people have discovered that many types of rocks, certain igneous rocks and even some iron-rich sedimentary rocks, retain a remnant of the magnetic fields that existed at the time they formed. And so we can recover that remnant of the magnetic field and figure out what direction the magnetic field was. There's some other things you can do about it. You could tell what latitude something was at relative to the magnetic field. We're not going to deal with that in this course. But we could tell the polarity as well. And it was discovered that the Earth's magnetic field flip-flops. Now, it doesn't flip-flop on a regular basis, and that's a common misconception. It's not every X thousand years it flips. In fact, it flip-flops on an extraordinarily irregular basis, and that is actually useful. If it did it like clockwork, it wouldn't have the advantages that it does in terms of dating. But because it's an extremely erratic system, it means we'll have periods of time of varying lengths of what we call normal, which is the condition today, and what we call reversed, Now, reverse is simply the opposite of the day. The world operates the same way. It's just if you took your compass back to those time periods, your north pole, the north needle on the compass would point south. And because these are often in igneous rocks, we can get a radiometric date for them, but we can also get the magnetic field. And we can see that here, for instance, there was a period of normal that goes back almost all the way to 1 million years ago. And then it flipped to reverse for a short period, then flipped a shorter time back to normal, and then flipped a longer period of time reverse, then a short normal, and so forth. And you wind up something that looks like the UPC code. I know the C stands for code. It looks like the bars on the back of an object you're trying to buy in a store, or your scan on the back of your ID card or what have you. And if you have a stretch of sediment, or a stretch of rock, sediment or otherwise, where you can get the polarities of the field, you can compare them one to another and match up these patterns. Additionally, when we add these up together from a relatively continuous record and through aspects of plate tectonics that we won't deal with in this class, the seafloor is a continuous record, at least for the later part of Earth history, and records magnetic fields. We have a scale that we can match them up, and we basically match up the longs and the shorts of the normals and the reverses to see where we are. Now, one real advantage of this is sometimes these flip-flops are over very short periods of time. In fact, it might be shorter periods of time than we could easily resolve with radiometric dating. And so we've got this, geomagnetic polarity scale that goes back in time. And just to show you how varied these are, so this is 66 million years worth of flip-flopping. The scale changes on this diagram, and this is 40 million years where it basically stays normal with a handful of reverses. So there's no guarantee that it's going to change within 10,000 or 100,000 or a million years. However, we get earlier and earlier in time and we have a less continuous record, so we can't actually correlate using that. Ultimately, when we want to really date a particular chunk of rock, so a real body of rock like you see here, you don't want to use just one thing. We want to use everything we have available. So we want to look at, what strata they are, what formations. We might already have some information about those ages. We want to look at the index fossils to see where they are in the biochronology, the biostratigraphy, the sequence of fossils through time. That might help narrow it down. If we've got ash beds or cross-cutting igneous intrusions, we can get some radiometric dates. And if we've got polarity fields from the magnetostratigraphy, that can also help us narrow it down. And in your homework, you can use a bunch of information to see how you narrow down when a particular horizon of sediment with a particular batch of fossils occurs, and then that can help tell you when they were in time. So, going back to the original answer to the question for this lecture, how do you know how old a fossil is? In general, you figure out how old the rocks in which that fossil was buried were. So when did those rocks form in time? That tells you how old the fossils are. Next lecture, we're going to talk about how fossils themselves form. And that we'll also use that as an opportunity to revisit this issue of paleo environments, what environments were like in the past. So I'll see you then. Take care. And again, welcome to the class.